This is lecture 22, a continuation of chapter 6. In this lecture, what I'd like to do is talk about the method of sections way of solving for trusses. And one thing we'll find that with method of sections is that, and as I mentioned at the end of the last lecture, is that you don't need to work through the entire truss. If you're only interested in sections that are in the middle, then this is the perfect method to do that. So before we jump into that, though, I did want to mention briefly the idea of determinate and indeterminate trusses. And there are a few pages in your book you can look at. And so first off is we talked about simple trusses early on, which are when you start with a triangle and then you add two members to that, and then two more and two more and two more. And so those are called simple trusses because they can be made simply by adding two members to an existing triangle. Sometimes, though, when you take two simple trusses and put them together, though, you create what's called a compound truss, in which case it's no longer a simple truss. Now, whether it's a compound or simple truss, in order to do the analysis, they've come up with this rule that says m equals 2n minus 3. Now, what m represents is the number of members, and n is the number of joints. So if you have it such that you count up all the members, and then you count up all the joints, and it works out to be equal in this relationship, that means that you can do the analysis. Now, just because it meets this doesn't guarantee that you're going to be able to do it, but if it doesn't meet this, then right away you'll know you can't do it. So it's kind of a required but does not guarantee. So the two trusses that I'm showing A and B here out of your book, those are both trusses that could be calculated using the conventional methods. They both follow the m equals 2n minus 3 mode. Now, if we take the one truss and for whatever reason we decide it looks, we don't like the way it looks asymmetrical without one BE, or we want to add CD to it so it looks more uniform, the addition of that makes this truss indeterminate, because now the number of members is greater than 2n minus 3. And what this really comes down to is we have more members than equations. So when we go to solve, we may find that at a certain joint, there'll be more than two unknowns at that joint. Because remember that with method of joints, we can only solve for two unknowns because we only have two equations, some unknowns at the x, some unknowns in the y. And so this is an example of how it becomes indeterminate. Now, just because indeterminate doesn't mean you stop there. It's just that in this course, we don't have the tools in which to solve. And that's something, if you end up taking a more advanced class in structures, if you're a civil engineer, you'll definitely get into this. It just depends on the path you take. But for our class, we're only going to deal with determinate trusses. Another concept too is if you have the equation, instead of being greater than 2n minus 3, it's less than 2n minus 3. So in that case, you're determinate because you have enough equations compared to the number of members, but the truss may not be rigid. So for example, if you look at these two trusses here, and of course we have to include the reactions at the bottom, and so the left truss has A and F both having an X and Y component, whereas the truss on the right has a roller, which is what we're used to seeing. But if you think of this practically, if the joint B can support no rotation, then any force that you apply to this truss is going to cause it to collapse. Basically, F will move to the right and the truss will not support the load. So that's it in a nutshell. And so I would review that. It's not something I'm going to test you on. It's just more of a concept that may come back in future classes, but it leaves the idea of something that's essentially something is indeterminate, means that you can't solve for it. You could have, sorry, I got distracted there. And you can have non-rigid. So either situation isn't ideal. So we're dealing with rigid determinate trusses, and that's what you need to understand. Okay, so method of sections. Now, as I mentioned, is that the method allows you to go ahead and calculate calculate a section that's in the middle of your truss. And so this example, we've taken this truss and we've cut it down the middle with cuts NN. Now you'll notice that when we do that, we essentially can eliminate one side of the truss. In this case, they've eliminated the right side of the truss, but there's nothing to say you can't eliminate the left side of the truss. Whichever side you eliminate, you no longer have to worry about those forces or reactions. So in this case, since they eliminated the right side of the truss, we only care about the loaded A, the loaded B, and the three forces that were cut. Now, if you look at this, you can see that if I were to sum the moments at B, that would get rid of two of my unknown forces, and I could then solve for CE, because then I would just know that the loaded A, which would be a given, would have to oppose CE. So you should be able to visualize this, but that would mean that C would not be pointing to the right, it would be pointing to the left, because in order to keep that in place, the force would have to go to the opposite direction. So CE would be in compression. Now, once you had that, then you could sum moments about another point, or you could sum forces. So one of the things you'll notice right away is that BE is the only of the two unknowns that has a Y component. So if you didn't even want to start with summing moments about B, you could have started by just summing the forces in the Y, and you could have solved for BE directly. So once you had BE and then found CE, then you could have summed the forces in the X and solved for BE. So that's easy to say in words, but let's actually look at an example. So here I've I guess I actually talked over myself, but this is what I meant to say. So here you can see in writing what we were going to do. So the force CE times the distance BC plus the P1 times that distance AB equals 0. Sum the forces in the Y, you get P1 plus P2 plus the Y component of BE equals 0. And then lastly, X, BD plus BE, X component plus CE, all equals 0. So the three equations I've listed, you'll have to, through practice, figure out which one you do first, but you'll always be in a situation where you'll have enough equations compared to unknowns. One of the things about method of sections, though, is to remember is you must always cut completely through the truss. So you can't just cut a couple of numbers and call it good. You have to completely separate the truss from the other side, for the other half, I should say. All right. So here's a real example. And so we have 36 kips on either side at D and F. And so first thing we're going to do is we calculate what is the reaction at A, what is the reaction at H. So if we do that, we can sum the moments at H, and we can determine what the reaction at A is. And so let's say we do that. So we do that, and we find out that the reaction at AY, or A, and it turns out there is no AX because there's no force applied, as you may have noticed. So we have AY equals 27 pips. And we have our cut. And so we're interested in finding specifically BD, CD, and CE. So we'll cut through those if the line is shown. And the one thing to note is that the CD slope is a 3, 4, 5 triangle based on the dimensions. So if you divide 7.5 by 2.5, you get 3. Divide 10 by 2.5, you get 4. So there's 3, 4. And so once we have this, then we're going to redraw it. And you get something like this. And so on this slide, I've essentially gone through the entire process and written out the answer, but you can take a moment to look at it, if you start with the right side, you can see where I've cut, and I've replaced the cuts with arrows, DD, CD, CE. Now, I've pointed them going away. That doesn't mean they necessarily are. That's just a convention. If you can draw it any way you want. If you want to draw them in compression, so be it. I've placed the small figure of what it looked like below for reference, so you can see the dimensions. So let's look at the first equation up here, Fy, sum of the forces in the y. We noticed again, just like the previous example with no numbers, is that CD is the only unknown number that has a y component. So we can solve for that correctly. We know that 3/5 of CD is the vertical component, so that has to be equal to whatever AY is. And so right away we see that both CD and AY can't be going up, so the arrow actually isn't going up, it's going down. So my assumption that CD is going up is incorrect. So CD is actually 45,000 pounds or 45 kips in the compression direction. So once we have that, then we can, and we could have done this other step first too. We could have summed the moments at C first, and that would have eliminated CD and CE. So as I'm pointing out, there's no specific way you have to attack it, unlike the method of joints where you usually almost always have to start at a corner, otherwise you'll end up with too many unknowns. With method of sections, there's usually some option. So in this case, if we do moment about C, we have just AY vertical force times distance of 10 feet to C. That's its perpendicular distance. And then we have a distance of 7.5 for BD. So we plug in the 27 kips times 10 gives us 270 kip feet divided by 7.5. That equals a negative BD. So BD ends up being 36,000 pounds in compression. So lastly, we go ahead and sum the forces in the X, and in that case, we just have CE minus BD minus 4/5 CD, because we've already established that BD and CD are negative, or compression going to the left, and we solve for CE, which ends up being 72,000 kips to the right in tension. So hopefully that makes sense. That's a pretty simple example. And all of the method of sections typically look like this. The only difference may be the geometry. Some of the geometries of the cross members might be a little more complicated, but otherwise they're very, very similar. Okay, so let's do a little more difficult example. And this one. And so here we have this truss, and we want to know what HI, GI, and GJ are. That's all we're interested in. So there's the red line that shows where I've cut the truss. Now at this point, I can choose to work with the left side of the truss or the right side of the truss. Either way, it'll come out exactly the same. I've chose to use the right side of the truss because it has less numbers, so the calculations will generally be simpler, less chance to make silly math errors. So if we go ahead and do that, and we cut it off, then let's go ahead and look at what that is. So leave that there for a second. This is also on the worksheet, so if you haven't downloaded the worksheet, please take the time to do so. It'll help you have this in front of you while we're working through this. Okay, so here is my drawing. Now I went ahead and I made my cut. So you can see I have my cut. There's H, G, and J. And what I've done is I've represented, I have dots here. Just these points still exist in space. They just, the loads on them, if there were, like an H, there is a load, it doesn't matter because it's all off in the area we don't care about. So the only loads we really care about are the ones over here. So I determined that the reaction at N based on the loading was 1,300 pounds, and then the 150, 300, 300, 300 was all from the original diagram. And these distances are 6 feet, and I don't have the other distances for the moment. The other thing is this slope of HI. If look at the geometry, it's a 2, 3, root 13 triangle. Not super clean, but that's what it is. whereas GI is a 3, 4, 5 triangle. All right, so what's the first step? So there's different ways to approach this. As I said, the first step, it depends on what you want to do. Now, and then my way isn't necessarily the only way to do it. But if I look at G here, it has I, G, or GI, and GJ, or JG, whatever you want to call it, goes through right to that point. So if I sum the moments about that point, I'm going to get rid of 2 of my rows. So if I go ahead and do that, sum the moment about G to 0, then what do I have? Well, I have my component of HI, right? Because I have to count that. And so and this is a triangle, so the horizontal component of HI is 3 over root 18 times HI. Now what's the distance? So the distance, of course, depends on where I'm taking that horizontal component from. Now, if I'm assuming compression, but again, the vector goes forever. So if I'm down here, I have a combination of an X and a Y component creating a moment, because there's both a perpendicular distance in the X and the Y. But if I back up my force all the way to just at H, then all I have is that, because my vertical component would go right to G, therefore would count. So what I can do then is I can just take this component, multiply it by that height, which is 8.5 feet. And in this case, because I've assumed it's compression around G, that's going to be a negative moment, right? Because it's clockwise. And then what's going to oppose that is going to be plus 1,300 pounds, because that's going counterclockwise, and its distance of 24 feet. I won't leave the dash off. It's improper, but 24 feet. And then the 300, they all account for clockwise, so minus 300. And then we have 300 at a distance of 6, at a distance of 12, and a distance of 18. So instead of writing 300 times 6, 300 times 12, 300 times 18, I can just factor it out, and then what do I have? I have 36. So that's just 300 times 36, okay? And then I also have minus 150 times 24. All right, count for that. And all that equals 0. So what do I end up with? I end up with HI equals 2,375 pounds. And I assumed it was in compression, and it's positive, so I was correct. So there it is, okay? So this really wasn't any different than the other problem, just a little bit more complicated in geometry, but really very, very manageable compared to other stuff. All right, so let's go ahead. Another way, sum the moments about I is 0. Now, if I sum the moment about I, that gets rid of HI and GI, so I can solve for just GJ. If I do that, then I get a similar type of problem. I get 1,300. Now it's only 18 feet away, right? Because I've moved now from H or from G to J, and so the distance from here over to here is now 18 feet. We've dropped 6 feet off of it, and so that's 13 times 18 minus, and then the usual 300. I'm not sure why it happened. Sorry. 300, and then that's 6 plus 12. If we're closer, and then minus 150 times 18. Okay, and that equals 0. Oh, and then of course we have to account for GJ. So minus GJ. GJ is where? It's in relation to it's a vertical distance of 4.5 feet. All right, and that all equals 0. So what we end up with then is GJ equals 3,400 pounds, and it's in tension. And that's what I guessed, and so I was correct. All right, so now looking at that, I have this, I have that, so I can sum the forces in the X or in the Y. If I sum the forces in the X, I don't have to deal with any of these forces. So if I sum the forces in the X, then I get minus 4/5 of GI. Now again, I'm assuming that GI is going left, or tension, and then minus 3,400 pounds, right? So 3,400 is this GJ, right, which I just solved for. So 3,400 going that way, the horizontal component of that going that way, which is just 4/5, and then so that in there, and then plus, because the other one is the vertical component 3/√13 of HI, which we know is 2375 pounds. So plug that into that all equals 0, and we get GI equal to negative 1779 pounds. So, which meant that it was actually in compression. So this should have gone that way, and so my final answer is GI equals 1779 pounds in compression. And there you have it. Okay, so that is the method of sections. So I think beyond that, we can do more examples. And actually, what I did is there are 2 worked examples that are of this difficulty, and I put them online. You can review those if you're still having trouble with the concept. Otherwise, in the next lecture, I may or may not do another method of sections, but definitely going to start talking about frames. So see you next time. Thank you.